Hey, this is a video for 8.12 and 8.13, LD50 and dose response curve. So go ahead and check out the overviews and set up your guided notes. So I joined these two together because they're both very closely related, but we have a lethal dose 50% and a dose response curve. The LD50, as it is called, is the concentration of a toxin or any pollutant that is required in order for 50% of the test subjects to die. And we measure this in, concentration and percent mortality usually. The independent variable is the concentration of the dose. It can be added to the air, to the water, or to food items. So oftentimes, especially with the red dyes that are found in Doritos and Takis, those are done by adding it to the food. Now we'll have our dependent variable, which is going to be the percent mortality. And that is the response to this dose. So if it's not mortality, maybe it'll affect germination. Maybe it would affect any other physical attribute of the organism. Now we will use special graph paper, and this is called semi-log graph paper. Instead of going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, we're going 1 through 10, and then 20 through 100, and then 100 through 1,000, 1,000 through 10,000. So every time we get to one of these major lines, we increase it tenfold. So what does that look like? Like here, it's 0.0001, 0001, 0002, 0003, 0004, and so on. And then once we get up here, we're 0.001, 002, 003, 004, 005, and then we get to 0.01, 0.02, 0.03, and so on and so forth. So notice here at these low concentrations, we have 0% mortality. Now, if I were to graph it, this resulting graph is my dose response curve. Now, to figure out the LD50, you need to first do the dose response curve. And you'll notice that there's an area where it starts increasing. And this is called the threshold. And the threshold is really where we start to see the effects start to appear. This doesn't mean that you can necessarily die if you took something at this concentration. However, the chances are, increasing that it could be lethal to some of the organisms. Now, we also, in order to calculate our LD50, you need to first figure out where is your 50% mortality and draw a line straight across, step 1. Then draw a line straight down, step 2. Figure out where this intersects with the x-axis, and that is your lethal dose 50%. So if we moved it up closer, it's right here. This is 0.01, 0.02. So this is between 0.02 and 0.03. And I'm going to say it is 0.022, and I'm going to express it in milligrams per kilogram. It could also be grams per kilogram, micrograms per kilogram. It could be in any unit, but usually it's per kilogram. And this is per kilogram of body tissue of the subject. So oftentimes we are testing it on animals because we do not do dose response studies on humans. It is too risky. We don't want to just say, hey, let's kill 50% of the people and, okay, there's our data. That's way too ethically not sound. So we will test it often we'll use models. So for mammals, we will use mice and rats. If we're testing aquatic reptiles and amphibians, we'll use fish. And if we're testing terrestrial reptiles and amphibians, we'll use birds. Now, we can use different organisms, but oftentimes a lot of these are, if you're testing drugs for pharmaceutical companies, you'll test it on mice and rats. We have similar body structures. I know that doesn't seem right, but we have common ancestors. So a lot of our organ systems operate in the same fashion. Now, if we're doing if we start with mice and rats, eventually a lot of times we'll use pigs, and pigs are even closer to humans. Their body structures are more closely related. If it's something that is really sensitive that we really want to test it, we can test it on chimps or other primates as well. Oftentimes it's expressed in milligrams per kilogram. So if we get like 5 milligrams per 1 kilogram of rat, we would just express, or we would just move that up, and we would express it in milligrams per kilogram for a human. So you would use dimensional analysis, proportions basically. So let's look at a practice calculation. So the LD50 of a particular chemical is 50 milligrams per kilogram. Calculate the mass of chemical in grams to elicit a lethal response in a 75 kilogram human. So what we know is we got 50 milligrams per 1 kilogram, and we have a 75 kilogram human. So we're going to set up a proportion. First, we're going to put in our LD50 for our test subject, and then we're going to put in this is the unknown amount that it would take to be 50% lethal for humans. When we solve for X, we will get 3,750 milligrams. And the other way you could show it, we're going to convert it into grams, and you have to start with milligrams and then convert the milligrams to grams, and it's 3.75 grams, because note they wanted the value in grams. Now, we use this for acute and chronic studies. Acute means short term, something like COVID. But if you get long-term COVID, that would be something that is chronic. But something that is acute is short-term. You might not have the effects of longer-term, long-term impact of something. If you're testing, for example, Advil, like you're not taking Advil, you're taking it for a headache, you're not taking it for, long-term treatment. So we might not have long-term data on Advil, for example. We also don't know the ecological impacts because we're not studying that for short term. For long term, we would maybe, for example, study fish from the hatchling to sexual maturity. So we would want to study something, or we could study rats from gestational periods until sexual maturity as well. So what I would like you to do is respond to this short, quick check for understanding. And for FRQ practice, explain how a dose-response curve can be used to determine lethal doses in humans. I hope that this video was informative. I thank you for your attention, and I will see you soon.